electrical conductivity of aqueous solutions, electrolytes and non-electrolytes, strong and weak electrolytes or non-electrolytes. What do you do when it's 8,000 degrees in the lab? Add in the possibility of electrocution. So that's today's experiment. Remember the definition of what an electrolyte is from the lecture, and that is something which, when dissolved in water, big part of the definition there, conducts electricity. So we have a conductivity tester here, which is just a wire plugged into the outlet over there. One wire down, break, no connecting the wire, other wire up, light bulb. All right? So if we connect the two wires electrically, say with a piece of metal, light bulb on, nice and bright. No connector. I could just connect the two wires together by bending them. Same thing, super, super, super bright, but same thing, all right? If we get a conductor in here, other than a piece of metal, say a solution of ions that are able to move, then we can have mobile ions allowing for the carrying of electrons from the wire to the other wire and lighting up the light bulb. So let's see what does that. Some things conduct strongly, those are strong electrolytes. Some things conduct weakly, those are weak electrolytes. And some things don't conduct at all, those are non-electrolytes. Now usually I like to get a variety of different solutions. I ask my son for a urine sample, he always likes peeing in a beaker for me. And we test that, and I test Gatorade and diet soda and regular soda. And I don't have any of that stuff with me today. So we'll just do the things on the list. And I apologize for that. All right? So the first thing up on the list is our deionized water. Again, this bottle says distilled water on it, but it is, in fact, deionized. We have a deionizer. In fact, I think I can get you a shot of it. Over there on the wall, those blue canisters take the tap water and deionize it. Now, New York City tap water is pretty darn pristine. If you drive upstate to some of the reservoirs up there, occasionally you'll see an NYPD car passing by or an NYDEP car passing by, because the city of New York owns those upstate reservoirs, much to the consternation of the folks who live near those reservoirs. So let's test our deionized water by, just for the sake of speed, filling up this 50 milliliter beaker with the deionized water. We'll use this to wash the electrodes off in between each experiment. So here we go. Blink. I have submerged the electrodes into the, not a solution because it's just deionized water. And nothing. No light. All right? So now it's up to you to go back and coordinate this with your lecture information and determine, is water an ionic compound or a molecule? Is it an acid, a base, a salt, or none of the above? What did you observe? Well, that we certainly can agree is no light. And therefore, what is your conclusion about deionized water? Let's try tap water, shall we? New York City tap water, again, very, very clean from those reservoirs. Let's see how clean it is, or whether the pipes leading up to this lab are clean or not. So, filled out of the tap moments ago. There we go. Nice clean water. And again, onto the electrodes. And again, whole lot of nothing going on. Okay? No real difference between the deionized water and the tap water. So again, I leave it to you to look up, is water an ionic compound or a molecule? Is it an acid, a base, or a salt, or none? We saw no light. And then what is our conclusion about tap water? Next up, sodium chloride. I need a paper towel to make sure that my electrodes are dry before I dip it into, you'll note that it says sodium chloride NaCl solid table salt. Top not stuck on the bottle particularly well. Alright, here is a jar of table salt. It's going to be too far down in there for me to reach with the electrodes, but I think I can shuffle it up a little bit, and let's see what happens. Not going to reach. Let's put it in a beaker. Nice clean beaker. Normally we shouldn't pour it back into our original container, but I don't want to waste the salt unnecessarily. Clean beaker. Fill it up with salt. See what happens. Nothing. Now you'll note in the final column, conclusion, strong, weak, non-electrolyte, I put a line through it so that you couldn't conclude anything about this. And the reason that I did that is because of the definition of an electrolyte. A compound which, when dissolved in water, conducts electricity. This is solid table salt. There is no water. It doesn't fit the definition. Electrolytes, like sports drinks, Gatorade, replace your electrolytes, because when you sweat, you're sweating out salts. You're not sweating out solid salts, you're sweating out solutions of those salts. It's replacing your electrolytes. Okay? We can't decide what this is because it doesn't fit our definition. There may be ions present, you will decide, based on sodium chloride being ionic or molecular. If there are ions present, when you decide that, they're not mobile. They can't move. They are fixed in place in the solid. And any electrons that have been transferred from the Na to the Cl are on the Cl now. And and the ions can't move. It's a solid. It's in a fixed position. So, not testable particularly. I left it in the lab manual, even a few editions on, because I wanted to make that point. So let's try sodium chloride dissolved in some water. 10% by mass sodium chloride in water. Again, notice I put the cap up so I won't contaminate my bottle. Back on. Now let's see what happens for this one. Okay, I didn't bother cleaning off the solid off the electrodes because it can just dissolve in the water when we put this in. Holy mole! Let's see if that's any different than just connecting it with a metal wire. If anything, it's brighter. Pretty much the same. Okay? So, very bright light when sodium chloride is dissolved in water, perhaps allowing for the movement of ions if you decide that this is an ionic compound. All right. Let's clean off our electrodes for the next one. Just put a little waste beaker underneath here. Should unplug this for safety, but we're not going to bother. And make sure we get the other electrode. As long as I don't cross the two streams, I think we're probably safe here. All right, nice and clean. Could dry it off if I want to. Okay, waste beaker. Next up, sodium bicarbonate, aka baking soda, but as the solid. All right, well, is this an ionic compound or a molecular compound? Same as the table salt? Still doesn't matter. It's a solid. If there are ions present, and again I have to leave that to you to decide, they can't be mobile enough to allow a transfer of electrons from one wire to the other, to allow conduction. So it doesn't work. Nothing. Again, I put a line through that final column because it is a solid. We can't test it. Not validly. How about a 0.1 capital M solution? That's 0.1 moles per liter. Hopefully you've gotten to moles in class. But you would figure out the molar mass of sodium bicarbonate, weigh that out in grams, add that to a liter, or make it up to it, technically, not adding it to a liter of water, but making it up to a liter of solution, and you have a 1 molar solution. This is 0.1 molar solution. So you would take 0.1 times the molar mass, add it to enough water to make a liter of solution, and that would give you your 0.1 moles per liter solution. All right, what's that going to be? Again, I didn't clean it off because it is the same stuff dissolved. Bright light again. Looks like this might be Na plus HCO3 minus ions in this ionic compound, allowing for very strong conduction. And therefore your conclusion is it a strong electrolyte, a weak electrolyte, or a non-electrolyte? Give our electrodes a rinse. Sugar is next. Sucrose, C12, H22O11. Sugar, sugar, Let's test it in our thing. Nothing, because it's a solid. At the atomic level, there are huge spaces between the particles of this sugar and that sodium bicarbonate and that table salt, and there's no way an electron can hop across that huge distance. So it doesn't matter what it is. If you test it as a solid, you cannot determine if it is an electrolyte or not. So there's no point really in testing solids. I don't know why I put them in the lab manual, but just to make this point, you've got to satisfy the definition if you want to test it. So let's try sugar water, a sucrose solution. Bottoms up. Nothing. Absolutely no light. Why? Well, do we see any metal in sugar? Because normally for an ionic compound you have a metal cation, or ammonium as your cation, and then some sort of anion. Maybe it's a halogen like Cl minus, maybe it's a polyatomic ion like HCO3 minus bicarbonate, or CO3 2 minus carbonate. We don't seem to have that in sucrose. It's just C12H22O11. There's no metal. So maybe this is not ionic. I leave it to you to decide. But our sugar water definitely has no light. Let's rinse it off anyway. Alrighty. Next one. Ethanol, aka drinking alcohol. Very concentrated first, and then we'll add a little water to it and see what we get. Drinking alcohol. Don't drink it though. Don't drink anything in the lab. Test. No light at all. Nothing. Shadow it as much as possible. No light at all. Alright, well what happens if we add water to this? Make it an aqueous solution. Make it into a beer instead of Everclear. Add a little water. Make it ethanol aqueous. Well, ethanol didn't conduct, no light. Water didn't conduct, no light. A mixture of the two? What do you think? No light. Nothing. Right. Glacial acetic acid. It's a weird, very concentrated but weak acid. there are only 6 strong acids. HCl, HBr, HI, those 6. Oops, I wanted to put this in a big beaker. I'll start it with it in a small one. Why not? HCl, HBr, and HI. Nitric acid, HNO3. Perchloric acid, HClO4. And sulfuric acid, H2SO4. But only the first H counts for the strong acid. So this is a weak acid. Well, weak acids, sort of giving away the punchline here, are weak electrolytes. There are not very many ions present. Remember, an acid gives you H plus in solution. A weak acid doesn't give you very many H pluses in solution. It stays molecular. So let's see what we get. I don't see any light there at all. No, I can't even see the filament. Let's see what happens if I add water to this. Nothing. Ethanol and water mixed together, nothing happened. Acetic acid and water. What? It's hard to tell in the video. It's a little hard to tell in the video because of the white balance. The light is definitely getting brighter the more water I add, which is interesting. That didn't happen with ethanol and water, but with a weak acid like acetic acid, the more water I add, let's see if I can do it in a bigger beaker. Try and show you. Dim light, all right, a little bit. If I add more water, it gets brighter and brighter. It's something beyond the scope of this course. It's even beyond the scope of 151 General Chemistry, called the Ostwald dilution law. It's a special application of something called Le Chatelier's principle, which we do cover in this class briefly towards the end of the semester, in that the more water we add, the more ions we get. But that only happens for a weak electrolyte. If I did this with sodium chloride, it's already bright, and if I add more water, it can't get any brighter. It's already as bright as it's going to get. That's the difference between a strong electrolyte, or one way to tell the difference between a strong electrolyte and a weak electrolyte. A weak electrolyte, the more water I add, the more ions I get, and the brighter the light gets. If I do that with a strong electrolyte, it doesn't change, because I already have the maximum amount of ions that I'm going to get. It doesn't ionize any further. No more ions occur when I add water. Because of Le Chatelier's principle and the Ostwald dilution law, if I add more if I add more water to a weak electrolyte, I actually end up generating more ions. Let's try it with ammonia, which is a weak base. I'm giving away the answer again. Weak base. Let's add some to this beaker. Little one. Ammonia is smelling salts, so it's blasting me in the face right now. Again, hard to tell because of the white balance, but this light is very, very dim, just for comparison. Here's conductor. Here is weak electrolyte. Let's see what happens. Oh, I gave you the answer. Weak base. Let's see what happens as I add more water. Brighter and brighter and brighter. Indicative, as I said, of a weak base, because when I add more water, it's technically a reactant in the ionization of the base, and I end up producing more product, more ions. Your instructor can explain this a little bit more if they like. But again, Le Chatelier's principle is a topic for the end of the semester. For us, all that really matters is if you have a strong electrolyte and you add more water, it doesn't change anything. If you have a weak electrolyte and you add more water, it seems to give us more ions, a brighter light, which is a nice little test. That's the ammonia. Next up, rinse off our electrodes. Hydrochloric acid. So we kind of had ammonia on there twice. Had glacial acetic acid and then acetic acid. Ammonia is only on the data sheet once, but we really had it aqueous and then we added more water to see what would happen. Hydrochloric acid, also known as muriatic acid. If you ever owned or worked at a pool, there for some reason is a lot on this cap. Makes me a little bit nervous. Wipe off our bottle. Hydrochloric acid, you might recall, is on our list of 6 strong acids. Let's see what this looks like. That is definitely equal to just the conductor, connecting those wires with metal. Strong acid looks like a super bright light. Nitric acid was also on our list of strong acids. Let's see what that looks like. Again, equal to just conducting it with a piece of metal. Took me many years of practicing this lab. Do not jump when I did this one because you heard it pop. Conducts very well. Nitric acid, again, was on our list of 6 strong acids. And therefore, strong acid, every single HNO3 molecule that's present becomes an H plus and an NO3 minus. And those ions can move around and allow for the conduction through that solution. If I add water to it, let's do it just for the sake of argument. I know I just cleaned the electrodes. If I add water, nothing. It's as bright as it's going to get to begin with. Adding water to a strong acid doesn't have any impact. Now if I added a ton of water, like a swimming pool of water, eventually the light's going to get dim just because the ions are going to be so far apart from each other. So the solution is going to be so dilute. But moderate dilution of a strong acid or strong base does nothing. Moderate dilution of a weak acid or weak base results in more ions being present, counterintuitively, and therefore a brighter light. So let's do some sodium hydroxide, which is a strong base. Pretty much any soluble metal hydroxide is a strong base. Bases give you OH minus ions in solution. This sodium hydroxide is 6 moles of NaOH per liter of solution. Now there's some chunks in there. Let's see if you can see them. Yeah. So this is a kind of an old solution. Should not have any chunks in it. Let's see if that impacts anything. Yep. Bright as bright can be. Solid NaOH is kind of hard to come by because it absorbs water out of the air. But you might have some NaOH lying around your house in a bottle labeled, or a can, labeled Easy Off Oven Cleaner is NaOH in a solution that will eventually dissolve that can. So that's why your can stops spraying if you have a really old can of oven cleaner. It's dissolved the inside of the can with a sprayer. Next up, after I rinse off my electrodes, is a slurry of calcium hydroxide. Now I wrote aqueous on there because calcium hydroxide is one of those ones where it's, in chemistry we present things as a lot of black and white, but it's not always black and white. So this, if I shake it, right, it's not all dissolved. There's solids sitting on the bottom. There's definitely some milkiness to this. This is not a white bottle. This is coated on the inside with this stuff. It's calcium hydroxide, tons. So the question is, in this metal hydroxide, has it dissolved, or did I just kind of shake it up and make a slurry of solid and liquid? So let's test it. Let's find out. Because if you have a metal hydroxide that doesn't dissolve in water, it's just like dipping the electrodes into a solid. Nothing can really happen. Let's see. Tums. I guess some of that stuff was dissolved. Didn't dissolve very well, but dissolved enough to give us an absolutely bright light. Is this metal hydroxide ionic or molecular? Is it an acid, a base, a salt, or none? Does it give us H plus in solution? Does it give us OH minus in solution? Does it give us neither of those but still ions in solution? That's the definition of a salt. Or is it just a molecule that happens to dissolve in water, like sugar? Oops, gave away the answer for that one, but we already passed it. Sugar dissolves in water great because it has OHs in it, just like water, HOH. Like dissolves like. So water will dissolve sugar wonderfully. Doesn't mean that it makes the sugar ionize. Calcium hydroxide, on the other hand, is an ionic compound, not to give too much away, and it's clearly enough of it dissolved in water to get us some light today. How about Mylanta instead of Tums? Magnesium hydroxide. Let's rinse off our electrodes. Look at this. Clear, colorless solution. Maybe some of it dissolved and the rest is just sitting on the bottom. Or maybe none of it dissolved and it's all just sitting on the bottom. Let's shake the heck out of this. If you ever take Mylanta for upset stomach, indigestion, then it says on the bottle to shake it. It's stuck to the bottom pretty good. But I think we got enough. Alright, if any of it dissolved, it's definitely dissolved, and there's certainly a little bit swirling around in there. Let's see if this, is it ionic? Is it molecular? If it is ionic, does it dissolve in the water? Is it going to conduct? I have a line through the end because it just doesn't dissolve in water. Okay? Magnesium hydroxide, actually I'm going to take it out for the next edition of the lab manual. But magnesium hydroxide doesn't dissolve in water, unlike calcium hydroxide, which does dissolve in water. So this slurry doesn't conduct. Does that mean it's a non-electrolyte? Absolutely not. That's why I put the line in the last column. It's an ionic compound, to give you the answer to the first column, but it doesn't dissolve in water. And if it doesn't dissolve in water, just like those solids we tested at the beginning, you cannot determine whether it is an electrolyte or not by this method. You can take the solid and melt it and then test it with this. It just would be really, really, really hot. But you could melt sugar, test it, no light. Melt magnesium hydroxide, like 800 something degrees, the light would come on because the ions would be mobile. There are no ions in melted sugar. There are ions in melted magnesium hydroxide. This is not melted magnesium hydroxide. This is magnesium hydroxide that is not even dissolved in water. Dissolving and melting are not the same thing. When we did boiling points and melting points experiment 2, we melted a solid. We didn't dissolve it in anything. Dissolving it in something is making it into a solution, making it into a mixture. This is testing whether it's dissolved. Magnesium hydroxide does not dissolve in water. Sugar dissolves in water but does not ionize. Melted sugar would not conduct because there are no ions present. Magnesium hydroxide melted would conduct because there are ions present that are able to move and complete the circuit. That is the end of this experiment. Massive cleanup of all these beakers. See you for the next one.